And okay. Officially now we start. Good morning, everyone. I hope you are safe and you are in good environment. We will continue this until administration see otherwise. Hopefully the situation will become better soon. Continuing with our materials, I have to move among screens, and as I said before I start recording, that if I say that I have something on my screen that it's not, please let me know. So now I'm sharing my screen, and which screen I want to share? This is first. So share. Okay. See, this is the Moodle page. If you don't see it, you let me know. And there is a handout 8. It's input and output. I'm gonna share it with you now. Stop sharing. Share again. I don't know if I can share at the same time. And this is the document. And share it. And there is a whiteboard there somewhere that I can share also. Share. Let me see if I can share the board at the same time. I prepared all of them here. Where are you? Whiteboard. I don't see any whiteboard. I don't see any whiteboard. I don't see any whiteboard. Oh my God. Okay. Okay. Whiteboard. Whiteboard. I need a whiteboard. Maybe I don't need a whiteboard. We will see. There is something down there. Well, I'm not sure. Waste of time. Bad, whatchamacallit, bad, close it, close the share. And you can still see my, here somewhere. This is supposed to be a whiteboard or something, no? I prepared it a minute ago. Is it somewhere at the back? Let me see if it's here somewhere. Here it is. So can you see the whiteboard at the same time with this, guys? Answer me, please. What do you see on my screen?
We only see the document input
The
output.
document, the whiteboard, no, huh? So
No.
if I say share, where will I get to?
Share entire screen will show the entire screen.
Okay, this is important. Now you see them? I was sharing
Yes.
the screen. Okay, great. Now we can start our session. Alhamdulillah. Here we go, guys. This link is the same document that I have here, but it's more colorful, and there are extra. Just click on it and read it, guys. It's a link to a different notes taken of input and output chapter. If you have any questions about it, you can talk to me, ask me about it later on, when we meet again. I forgot to tell you that I'm in my office. I give my lectures from Hagazian, and if you are close by, you can stop by. And at 12, I'll be available to go on Zoom one-on-one and answer your questions. We start. This is an I/O module, guys. It's an input-output, right? So I think chapter 7, input and output. I/O module sitting on the bus. You know the bus, address lines, data lines, control lines, all put into the I/O module. What is it? It's a hardware. It's a hardware that connects the CPU, the RAM, and the peripheral devices. Peripheral, all peripherals from input and output devices, whatever the device is, be it a keyboard, mouse, hard disk, whatever it is. So it's a hardware. And these devices, guys, of course, must be homogeneous. They should be of the same type. And you cannot put I/O module to service the hard disk and at the same time printer and at the same time keyboard. No. So there is a specialized I/O module for specialized devices, for different type of devices. Okay. Why do we need them? We need them because the devices, they deliver data at different speed, not at the same speed as CPU. Imagine someone who talks very fast and an output device that talks very slow. And of course, this needs managing. So time management there between devices. Different speed, we said, different amount of data. Maybe one of them will work at a byte rate and another device will work at a block rate. Command, this should be managed. And in different formats. This device can understand PRNT as a print, while the CPU instruction set can understand it as PRN without the T or anything like that. So this is why we need, guys, the I/O module to have all type of devices communicating properly with the CPU and the RAM. All slower than CPU, this is why I said timing is important, need an I/O module, it interface, and Okay, we tag. The functions, the same. Whatever we mentioned a minute ago, control and timing, CPU communication, device communication, data buffering, and error detection. What is that, guys? This is what's inside the I/O module. What does it do? It does all of this. It does data buffering. It means that there is a buffer for this. Why? Because the speed or the byte transfer. So the device will talk to the I/O module, and the I/O module will answer to the CPU at the same, at its time, at its format, and everything that's mentioned in here. Okay, I/O steps. It's obvious that the CPU checks the I/O module device status. Okay, we are checking the printer device status. I want to print something. So why I'm checking the status of the printer? Maybe it's off. Maybe it doesn't have ink. Maybe this and that. So all this will be returned from that device, here, the printer assumingly, back to the I/O module and back to the CPU telling it that I am out of ink. I am off. I am not there, or something like that. I/O module return the status. If ready, CPU request data transfer. Okay. I/O module gets the data from the device. Wait a minute. Here. If ready, CPU request data transfer. In or out, guys? Into the CPU or out from the CPU. So suppose the device here is a hard disk. Then you know that it's both of them. So you need the control line to say that I want to read or write. I want the data lines if I am writing. I am writing something. If I'm reading, the data line will be empty. And the address lines. Okay, the address lines of what, guys? The address lines first of I/O module. Why? Don't the CPU know the I/O module address? Yes, if it's only one I/O module. But we can have more than one I/O module sitting on the bus. So I/O module for example, printers, I/O module for the hard disk, I/O module for this and that. So we have to differentiate between them by giving them different addresses. So reading or writing, data lines are on if we are writing, they are empty if we are reading from the device like hard disk or something, and the address line, which tells which I/O module we are referencing and which device of the device is controlled by the I/O module. And then it is. Is that all, guys? No, no, no. We still need one part of the address line, which is what? It's, suppose you are reading from a file or something, from a hard disk, then you need the file name, you need which byte of the file name or which page of the file or which block of the file name you are reading. All this should be specific, guys. All this should be specific. Okay, so that was about requesting data transfer. IO module gets data from the device. So the device, once it's ready, the buffer is full, and now there is a long story about how the IO module will return the data to the CPU. And during that time, what would the CPU be doing? Are you okay? IO module is ready to return the data back to the CPU. What was the CPU doing during the time when IO module was collecting the data if the request was to read the data? Was it sitting idle? No. You remember when we were talking about interrupts? And then the CPU will send a request to the IO module. At that time we were saying to the IO device. Now we are talking about IO modules. So the IO module now sends a signal, you remember? Interrupt signal to the CPU, the arbiter will take place, and then the IO module will get the bus and then send back the data to the CPU to resume with the process that asks for that data. This part we know. So we are only introducing an IO module for the following functions to make that process possible because of the differences in the CPU speed, format, and blah, blah, blah with the devices itself. IO module gets the data from the device. IO module transfer data to the CPU and variation for output DMA plus. This is what we will be talking about mostly during the rest of this lecture. Because we already know what IO module, we already know the job, the function of it, and why it's supposed to be there. Here it is. Let me move it a little bit here. I don't know if you can see it, all of it. And this is the, I maybe need also it so I can see. IO module structure. This is, remember, it's hardware, right? There is a logic in it, IO logic in there. This could be a firmware, guys. This could be a software within the hardware because it could be a nested if statement similar to the instruction set that we did for Von Neumann. We have an instruction set for the IO module. If you are asked to do this, you do this. If you are asked to do that, you do that, and something like this. What are the ends to the IO module? We mentioned them a minute ago, guys. The data lines, the address lines, and the control lines. Wait a minute. I know that the CPU sent control lines to the IO logic to tell it what to do. Mainly read, write, check device, blah, blah, blah. Why the arrow back? Who's going to answer that, please? Why the arrow back? Anyone? We know that control units go into the IO logic to tell the IO module what does it need from the devices. Remember that these are the devices here, the input-output device. This is the IO module. By the way, it's also called IO controller. So, well, either name is okay. We see that control lines are going into the IO logic, which has all the instructions that can be executed by this IO module. So the line in is fine. We all understand. Why the line out? Why from IO logic we go out to the control? Why we don't just settle for returning the data that the CPU asks for? And look, even the data in and out, this is explainable command. Data in and out, because if you are writing to the device somewhere here, if you are writing to the device, then you need data in, and then it goes to the device. If you are writing, then it goes in. If you are reading from the device, then the device will send the data into the data registers, and then it will go out. This is explainable. Address lines, let me see if it's explainable. Address lines, the address lines go inside to tell which of these devices to the right I am talking to, as I said before. So command, this is legitimate. The address out also, please explain. So can anyone explain control lines out and address lines out? Anybody? Come on, guys. I feel like you are not hearing me. Just check. I'm checking. Can you hear me?
Yes.
Yes, okay. So no answer? No one.
Control lines would maybe be like to write on the address to change maybe an address, like the values of the address, and address lines to select a different address.
The IO module does not select addresses. And control lines don't do that. Control lines go back, guys, to tell of those signals. Where are the signals? Status. As we said, guys, the device is off. Then you see one way. I am off. I need ink. I need this. I need that. Blah 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 blah. It goes yalla 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 yalla. It goes, and then it tells it through the control lines. So the control lines are the signals that are coming from the device back into the CPU. As far as the address going back, guys, you know that we talked about arbiters, and certain IO module wants to talk to the CPU. So there you go. I am the IO module with this address. My address is this on the bus. You remember here? I can have more than one. So more than IO module can sit there. So the address lines will carry the address of the IO module in order to know which address for the arbiter is. Okay, طيب. I'm not gonna keep asking you لأنه it's very difficult to do it an interactive session like in class. So we know all those lines, guys, in and out, in and out, in and out, in and out, in and out. Control lines, these are the control lines that go in. You see? Are you ready? Blah, blah, blah. I want to read. I want to write. The status that I am not ready. I need ink. Blah, blah, blah. Or I am ready. What do you want? And the data in and out. Suppose you are reading. Now they differ. For example, if this is a printer guide device, then you don't see data coming out from a printer. So this is in general. So these are in general, but for specific devices, they might change. Okay, do you have any questions about IO module and all the lines that go in and the ones that go out? And what is the job of the IO logic? Look here, guys, external device interface logic. For each device sitting here, there is an interface device logic. So one printer, these are supposed two printers, guys, suppose two printers. They might have different interface. They are both printers, so they can be joined by the same IO module, yes. But when it comes to talking to them, one of them might, as I said before, the print can be PRN, the other one can be PRNT. Then the IO logic should know when it communicates with this IO device, what does it say? And for this IO device, what does it say? I think it's fairly simple and straightforward. IO module must be able to recognize and generate addresses with the device it controls, of course. Each IO module has a unique address, of course, or it controls more than one external device, a unique set of addresses come in. Okay, we just mentioned that. So address for everything, address for this device, address for this device, address for this module, address for another module. And the CPU should be aware of all of these. Now, input-output techniques. These are old, guys. This is old. But we just mentioned it to see how computer architecture progressed. Programmed I/O, CPU has direct control over the I/O module. Sensing status, read-write command, transferring data, CPUs for a module, weights. This is the most important word, guys, there, weights. Waste of space, waste of time. So if we go back here, yeah, here, or here, no, I see the IO module here. This is the CPU, guys. This is the CPU. Then an IO instruction, read or write, suppose for a hard disk comes in from the program. and it is sent to a certain I/O module on the bus to a certain device within that I/O module. What would the CPU be doing then? In programmed I/O, which is, as I said, old, the CPU will sit idle. The CPU will sit idle. At each cycle, it will ask the I/O module, look, are you ready to send me back the result? No? Okay. Yalla. At each cycle, yalla. This device here is working to sending the I/O module the answer, and maybe here a bit that it's ready. So the CPU will check that bit, yalla, 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 until it's ready. Then it will take whatever is in the buffer will be transferred through the bus into the CPU, and life continues. And this is, of course, waste of CPU time. Nobody talks about this anymore, guys. Okay. How does it work? CPU request I/O operation. I/O module performs operation. I/O module sets status bit, as I said a minute ago. CPU checks status bit periodically. Here, I said that. I/O module does not inform CPU directly. I/O module does not interrupt. Why? Let it interrupt when it's ready. There were no interrupt scheme before that. ما في interrupt scheme. ما كنا عم نستعمل interrupt. CPU may wait or come back later. Okay, okay. We said at each cycle, it checked that bit, that status bit. This is all, just forget about it. But it's in the material because the computer architecture evolving. Interrupt-driven I/O, this is what we have been talking about from the beginning of this semester about interrupts, but we were talking about interrupts in general. Now, we are specifically talking about I/O interrupt. Then it could be different. Check, division by 0 is an interrupt, higher priority job is an interrupt, and so on and so forth. I/O interrupt overcomes CPU waiting. So CPU does not wait. Once it places the order to the I/O module, it just, what does it do? I have to wait for an answer for this, guys. What does it do? An I/O request comes from a process. What happens? Two words. CPU will put the request to one I/O module and context switching. Programmed I/O does not have context switching. Interrupt-driven have context switching. So the CPU moves to work on another process, and the I/O module will work on the process request. And when it's ready, it will send an interrupt signal, and we know the rest. No repeated CPU checking of the device, of course. No, the I/O module will request for bus grant and get the bus to transfer the result to the CPU. I/O module interrupts when ready, frees up the processor to some extent at the expense of I/O transfer rate. Okay. Here, why they are saying this, guys? Because free up the processor to some extent, the extent of I/O transfer. Then the processor is working very fast on one process, and then you interrupt him to send data. Of course, sending data is of less rate, so this is why we say CPU is wasting some time there. But it must happen. It must happen. How does it work? CPU should read the command. I/O module gets data from the peripherals, while CPU does other word. I/O module interrupts CPU. CPU requests data. I/O module transfer data from the buffer. You remember? From the buffer. The buffer was ready to send the data. We have been talking about this before, guys, but still, let's talk about it. Like context switching, save context. I just mentioned that. It's the same material, guys. We have talked about this, but instead of talking about interrupt in general, because مثلا division by 0, guys, ما في context switching. Interrupt, you just tell the operating system to tell the user you are out, fix your program, and then continue with its life. Here, it's a different story. And remember, guys, many devices on many different I/O modules, the CPU have to deal with that. Device issue an interrupt signal to the processor. Interrupt to processing. We did this before. Interrupt to the processor, guys. Change this word into something else. Come on, I'm gonna wait for an answer. Come on, guys. Any other word you can place here? Come on, anybody. Replace this word with a possible word. Possible. No one? If we were in class, everybody would be jumping and answering. Yasser, are you there? Yasser? No? Let me see. I don't know. Oh, where am I now? I lost the screen. So this one I can minimize. Oh yeah, yeah. We can change it with an
The
arbiter, guys.
CPU.
To the arbiter, yes. No, processor is a CPU.
Yeah.
I'm not talking about English. I'm talking about what we have seen in architecture. That could be the arbiter. And as we mentioned before, the arbiter could be a part of the processor or a separate part or a chip on the motherboard. So we could say here the arbiter. Processor checks for interrupt all the time. We have seen dedicated, non-dedicated, daisy chain, and something indicated by an interrupt signal. Okay, interrupt request or interrupt signal, guys. They mean the same thing. If no interrupt, fetch next instruction and continue with your life. We have seen this in the instruction cycle, if you remember, at the end of the cycle. If interrupt pending, we have seen what happened. Suspend execution of current program. Save context. This is context switching, as we said before. Context switching. Save the PC, the MAR, the MBR, blah, 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 everything, all the registers, guys, that are in the CPU, save them somewhere into the memory, and then bring back the job that's doing the I/O, the process that's doing the I/O, fill in the register in the CPU and continue. Set PC to start address of interrupt handler routine. Before that, yes, we have to check what kind of interrupt we have. This interrupt handler routine, or what do we call it? IRS, interrupt, ISR, interrupt, ISR, interrupt service routine, process interrupt, restore context switch, and continue interrupted program. This one was saved before, you see. We have done something similar before. Multiple interrupt, we talked about, guys. It's the same, it goes here the same way. So you can disable interrupt, you remember? I don't, operating system order, guys, processor will ignore further interrupts, but who is controlling this processor? تعرفوا, it's not his job to control. His job is to fetch, decode, execute, صح? So when we say processor will ignore further interrupts, because the operating system actually is disabling interrupt. So this is the idea. Low and high priorities, we talked about that also. Here, this is the most important part, guys, in what's happening now these days. Direct memory address, DMA, is a chip on the bus, on the system bus. Direct memory access. So I don't know if I can draw here something, guys. But it is drawn somewhere. Why should I draw it myself if it's there somewhere? Yeah. So this is the processor. But we have to place the whatchamacallit. We have to place them. And this is the memory. Yes, the memory is there. But I wouldn't draw it like this, guys. I would draw the memory closer to the processor. But it's just the idea. Here, we are not going daisy chain and something like that. It's not like that. Each of these has its own address. Memory has its own addresses. DMA has its own address, and I/O and I/O. Now, DMA is a chip. It controls I/O. So it's an advanced I/O controller, or advanced I/O module, you can say. So DMA controls I/O. Now, who's gonna tell me? Or I tell you, حتى we don't waste time, guys, on the recording, and we make it less space for it. So the DMA here is controlling these I/O devices. Great. In another form, guys, DMA control this, and another DMA control other I/O devices. So different ways. But let's concentrate on the DMA job, whether it's this one or whether it's this one, whether it's this one, it's the same, guys. Okay. Processor will ask the DMA. It will send the whole request, guys, not like one read. So in interrupt driven, if you are reading 1 byte, so if you are reading a block or you are printing information like a page in the memory or a file in the memory, then the processor will interfere with the I/O module at every request. Let me go back here. Let me go back here. CPU here. And the printer is here, guys. The CPU wants to print something from RAM into the device. Then it has to go according to transfer rate, byte by byte or block by block. Suppose byte by byte, and you see how difficult that would be. Then the CPU will send a request to the I/O module, print this byte from the RAM, and then the I/O module will pick it up and will print it through the printer. And then the CPU will interfere again, get another byte, and to the I/O module and print it. And during that time when the memory is sending to the I/O module and the I/O module is using the printer, the CPU can be doing something else. But you see how short period of time it is. It's very short period of time because you are printing only a byte. Okay, we continue this and it goes until the whole block is printed. Now listen to this. The DMA is capable of taking the order, the whole block, the order, the starting address of the data in the memory, and the length of the data to be printed from that location. Let me see. Do I print here? So can you see this, guys? Please let me know. So this is the RAM. Anybody? Can you see this while I'm wasting my time? What I'm drawing?
The drawing?
I'm drawing something, yes.
No, we cannot see it.
Oh, let me see. But I thought I did share this one. طيب, wait a minute. Stop sharing. And sharing again. I want to share again. وين راحت هلا? Here. Share again. Can't I share the, whatchamacallit, the, you know what, it might have been, hi, whiteboard here. Can you see the whiteboard now? Anyone? Whiteboard drawing, no?
No.
No. Let me see if I can share it now. لأنه where do I go with the share now? Here. So now I want to go back to the share. Share. No. The sharing. Close this. Now the sharing again. If I can, then I'm gonna drop whatever computer architecture. No. I can see it. I don't know. It's not anywhere. Wait a minute. Suppose on my screen, and then I should be able to. Where is my screen? Where is what is this? Yes. So let me see now if I can share my screen. It's jumping back and forth. So no. This is my screen. So if I say share my screen, will it share? I don't know. What happens now?
If you share the entire screen, we'll be able to see everything.
I shared it when Mark said that. I shared it. Now, can you see it? Can you see the whiteboard now? No. It's in front of me, guys. The,
We
the
can
whiteboard.
only see the cursor, not
I know.
the whiteboard itself.
Not what I'm writing, eh? Okay, so
No.
whiteboard again, whiteboard again. I don't. So I need to learn how to make the white. Oh, wait. I see a share on the whiteboard. Wait. Share what? Contact. I share with you. Oh, wait a minute. Now I should share the link. Copy the link. Then what? Only people with access. طيب. Only people with access. Only user account with Hagazian. طيب. شو copy link and so what? Copy link وبعدين شو ببعته يعني؟ Contact channel. Copy link وبعدين where do I send it to you? I don't. بريم وهبة. شو خصني بريم وهبة؟ No. I'm wasting my time. I'm wasting. Maybe I should do this at my time. خلاص بدون this without sharing this. We continue with our lecture, guys. Here I'm sharing my now. Can you see my screen back? Can you see the lecture, guys, where I was talking about? Answer me, please.
Yes.
Yes, great. Thank you, Mark. So here, خلاص. What can I say? I wish I can draw here. Is there a line to draw here? Let me see. Draw. Oh, I hope that my laugh on the recording sounds like I'm happy enough. So I'm sure now you can see, right? So this is the RAM. Yalla, we resolve things as they come. So this is the starting address of what I want to print. This is the data, and this is the end data. So the processor will send the DMA, the starting address, and the length, or the end address, ما بعرف, or the yeah, either way. I wanted to print from here to there. It's not a byte, guys, it's a whole block. And then processor go and does what? Context switching. اتفقنا؟ Now, what would the DMA do? The DMA should go to the RAM, get some data, and send them to the I/O module to be printed by the I/O. I think this is clear. So listen to this. The DMA will go using the bus to the RAM. RAM هي هون. To this address. Pick up data, byte of data or something. We will say what it is. Not pick the whole block, guys. It could be picking the whole block. It depends. I will tell you in a minute how. So pick up maybe a byte and then go back all the way to the DMA. And then listen, in this case, when you have single bus, then ask for the bus again. It will not transfer directly to the I/O module to print. No, it's controlled by DMA. So the DMA will ask for the bus again and send it to the I/O module, and then the I/O module will print it on the printer. Okay. How many times the DMA used? How many times it used the bus in order to print a byte or more than byte? I don't care. Twice, 2 times. CPU is working on something else. But how can the CPU here? How can the processor home? How can the processor be doing something, running another process if it's not getting the data needed from the RAM? Or from the cache. هون كمان في cache, guys, remember? Cache. Okay. Level of cache. بتقول يمكن هون. There could be something in the internal cache, level 1 cache. So the processor can be working inside, not using this bus. So the DMA will take that opportunity to use the bus to get the data from memory to itself, and then use the bus again into sending it to the I/O module, and the I/O module will take care of it. And then answer back the DMA, and life continues. In this case, we need only one access to the RAM. Look here. The processor asks the DMA, DMA will go and get the data needed, and then it goes back to the DMA, yani one bus access, guys. And then the DMA does not need the bus to send the data to the IO module to send it to the ID bus. So in this case, we need two accesses, two bus access in order to get a data transfer, whatever the unit is, as I said, byte or block or word. And here it needs only one time from memory, get it back, and then do it. Okay, great. Now, we stop the drawing for a second. Let me see if there is something there. Transfer كله تمام. Another DMA, guys, with a bus. These are different setup of the DMA. This is most advanced. مش هيك? DMA has a bus to all of these instead of DMA to one, or DMA has communicate with each bus separately. So we have a bus. So they are different architecture for the DMA with the IO modules and then IO devices. تمام. Let's concentrate now on talking about transferring data to the DMA from memory in order to get something done. Whatever I'm saying, guys, about printer, it's the same for disk reading or even writing, right? So whether I'm writing to the RAM, I should have where I'm writing to the RAM, the length of the data that I'm writing to the RAM, the data that I'm writing to the RAM, and in the buffer of the DMA, and then the communication will happen between the DMA and the RAM to transfer data back and forth. I think it's better to talk about this لأنه هون 2 times خلينا بال1 time here. So here it goes, guys. We have 3 ways for the processor. Let me go back to drawing. Oh, this is not drawing. Please, one more time. Yeah, this is drawing. Processor places an order to the DMA, goes to doing something else on process 2. Right. This established. Now, first method called cycle stealing, guys. Cycle stealing. If the request is like 1 byte, then the DMA can ask the processor to hold its breath for 1 cycle. Then it gets the bus, control of the bus, goes to the RAM, gets the data, and then everybody will continue doing what it needs to do. Cycle stealing, it's 1 cycle, 1 CPU cycle. Processor, hold your breath. Don't use the bus. I want to use the bus. DMA will go, and then خلاص, it will continue because it gets the data that it wants. Very short data, like a byte. Cycle stealing. Please write this down. It doesn't show here, and I don't want to waste my time writing them like cycle stealing. I'm sure I can write text here somewhere. No, I don't know. I will see it. So cycle stealing. I'm not gonna write everything. So this is what happens in cycle stealing. What's the benefit of that, guys? What's the difference between cycle stealing and interrupt? Anyone can tell me? What is the difference between cycle stealing and interrupt? Then we have seen interrupt a minute ago, right? Is it the same as interrupt? You can tell me that. It's the same as interrupt. Whether you interrupt the CPU for for 1 byte or for a whole block. What's the difference? It's an interrupt process. And the answer is no. The difference here is that the processor will not do context switching, guys. The processor will not do context switching. Interrupt, the processor will do context switching. Put the old process in and then answer to it and then go back to the new process. context switching is not happening here. Processor is holding its breath. Don't do anything unless I'll tell you why. It could be doing even something there. If it meets the bus, then the processor agrees to, okay, I'm gonna hold my breath. I'm not gonna use the bus for the next cycle. DMA will use it and everybody will continue with its life. This is called cycle stealing. The benefit is no context switching, processor hold, not use the bus for one cycle, and everybody will continue working. The second method, called transparent mode, transparent, whatever, transparent mode, yalla, transparent mode. I told you a minute ago that the CPU will hold its breath. What if the CPU is not using the bus from start? How could that be? Can the CPU not using the bus for a cycle? No, it's always hungry for the bus, the CPU. Yes. At one time, the processor could be doing something on its internal ALU. You know, the processor has, CPU has ALU and control unit and so. So he's adding two numbers, multiplying two numbers, During that time, it will not be using the bus. If it wants something from the internal cache, it's not using the bus. So the DMA at that time can take its what? بياخد مجده for one cycle, two cycles, and it will go to the RAM and gets the data needed, send it, and come in, we continue our life. This is called transparent mode. Okay. If the data is very large, you see here, we were talking about a cycle or two, يعني, or three, for the processor in the transparent mode, يعني, some data, مش 1 byte, and 1 byte cycle stealing is enough. For more than transparent mode. If you are transferring a large block of data, then it's not like 2 bytes or something, and the processor, no one can say that the processor will not need the bus for a long period of time. When we say long period, yeah, very short in CPU term. So in that case, we go to a mode called IO burst, IO burst mode. IO burst mode. Please, these are not in your notes, and maybe they are not in your book even, or in slides. I want you to know about them. Cycle stealing is mentioned everywhere. Now these two are new, and I'm explaining that to you directly. When the data to be transferred is too much, then the DMA, if allowed, will ask for the bus for a longer period of time. For longer period of time, it's not because the CPU does not need the bus. It's not because it's one cycle, because of cycle stealing. No, I want the bus for 3 or 4 cycles, and then the CPU will hold its breath. And this is a waste of time for the CPU, by the way, but life keeps going, and when the transfer is finished, CPU can continue. In 3 cases, guys, remember, no context switching. This is the main advantage of DMA, whether cycle stealing, transparent mode, or IO burst mode. Is there any question on this? This is the major idea, other than introducing IO module or IO controller and their functions and their structure. This is the most important part of this chapter, guys. Interrupt cycle is still there, but most likely the interrupt cycle is when the DMA is ready, and then it will want to tell the processor that it's finished. I'm talking about IO now. Then the DMA will have to go back to the processor and say, I finished my job, So I'm waiting for other requests now. Fine. That's it. That's it. That's it. If I go here, guys. Uh-oh, what? Leave what? What? Leave what? Leave site? What site? Changes that you made may not... Okay, leave. شو علي بدي شوف. Can you see now my screen ولا لا? The link that I went into. Can you see it?
Yes.
Yes.
Great. So guys, colorful, it's the same. Interrupt, IO module, DMA with colors, same. I'm just looking for asynchronous notes that will help you in everything we do. شو بطل بده؟ ليه وقف؟ skip add. Okay. فكرت لأنه ما وقف معي. IO module, peripheral communication. Here, the same. This is, I don't know, Chinese, I don't know. Anything I didn't mention, guys, you might not take into consideration a lot. So this is colorful, more detection and processing. IO module, this is very important. Like I talked before, this is colorful. You can see it colorful. And here there is something extra that only if you are interested, guys, in checking these things. Like here, this one, if you want to make sure that zeros and ones, and this is for engineers, mostly not for computer science, but you can go and see these if you want. And more than that, you can go and see the bit. These are the pins, guys. One pin at a time. Interrupt controller, guys. But this is engineer. It's not for us. I just put it there. If anybody is interested in engineering, in how chips like كل pin, what does it do? Each pin, like هذه البن, read or write. You see, one pin for read, write. هي 5 36. Okay. And that would be it. DMA is mentioned here, direct. Here, you see DMA is mentioned. Look, I have to tell you that this is important, guys, because this is in your chapter, and this is not in the previous note that I explained. I'm explaining it from here now. What is this for? Can I take it off without a fire? So this is part of the material that you're responsible for, please. This is the DMA structure. So it sits by definition. Where does it sit? On the on the system bus, and from the other side, there you have the IO module, and then the IO module communicate with the IO device. Tamam. Data lines. Now, instead of connecting the system bus to the IO module, you connect it to the DMA. So this is the DMA structure. Address line the same. Request, whole control, guys. These are the control lines. Like بعده الانتربت going out. Read or write that I told you when I showed you in the structure of the IO module. So mainly these are the same input. They were going to IO module. Now they are going into the DMA. Data count, what for? What for? Data count, guys. If you have a block to transfer from memory to a device, back and forth, from hard disk to memory or memory to hard disk, we said that the DMA will receive the starting address and the length, and this data count will keep counting how many data has been transferred so far, and then when the data completes, then it will inform, the DMA will inform through an interrupt request to the processor that I finished. Data registers the data received. If there is data to be written to the RAM or any other device. Okay, one more time. And data in, if there is something that should go back to the processor. Address register, of course, always address is there. RAM address, شو اسمه, hard disk address, and so on and so forth. And this is the control logic. So it looks very much similar to the IO module. The IO module is still there before the device, but this is the most important part, is the data count, which because we said here we can use this to free the processor to doing something else. The I/O module or I/O controller was not able to do that. So this is the chip the DMA is doing. This is the job that the chip DMA is doing. Typical DMA. This is on your slides. Don't forget to go through the slides, guys. Anything that you don't understand from the slides, you talk to me about. But this is the end of it here, DMA cycle. Okay, and this we have seen before. So, okay. I'm going to stop recording. First of all, حتى ما نكبر so stop recording. And are you sure you want to stop recording? Yes.